Okay, now we're going to talk about a topic from chapter 2 called gradients. This is new. It doesn't have much of an extension to R2. We can compute gradients for R3, R4, higher functions, but we're going to spend most of our time talking about gradients in R3, of R3 functions. So let's take one that we've seen before. F of xy is 6 minus x squared minus y squared. Okay, hopefully you're at this point in the class, you can visualize what that thing looks like. If not, you could definitely do a contour map and draw that, or you could take out a tech tool and visualize it. Let's quickly go through my thought process on how I visualize this. So this is related to z equals x squared plus y squared, which is that circular paraboloid opening up from the origin. And then z equals minus x squared minus y squared just inverts that thing, and it goes downward facing from the origin. And then taking 6 shifts that thing up 6 units, so that's 6 minus x squared minus y squared. Takes that downward facing circular paraboloid, and again, extends infinitely down that way, but it goes through right here at 6 on the z-axis. Okay, so we're going to compute something called the gradient for this. So you got a visual in your head what this function looks like. It's this downward mountain of downward facing circular paraboloid. And the gradient is just pieces of the partials. It's actually a vector of your first partials. So you're going to take your partials and then you're going to stick them in a vector. Okay, well, we've done some vector stuff in chapter 1, and this is just an extension of that. So I need to get my partials. Really easy function to do that for. Start off easy. Okay, so I got both first partials. I'm going to put those together in a vector, and here's the notation for a gradient. This upside down triangle, F, means, or you also see it written grad of F xy. And that just means the same thing, right? Those are the same thing. They mean compute the gradient, and the gradient is your vector of your first partials. And so you put the f sub x here, and you put the f sub y here. Easy one, minus 2x minus 2y, so it's a pretty simple vector to look at. And notice that this gradient is it's a vector function. So we haven't seen those yet, and we'll see them a whole lot more in book 3.5, but it's our first vector function, which means it takes as input an x and y, and it spits out a two-dimensional vector. Well, let's go ahead and graph a few of these vectors at particular points to try to see what's happening here. Okay, well okay, so I'm just like following instructions. I took gradients, I put them in a vector, but what is that really doing? What does it mean? So let's go ahead and evaluate this at, let's say, the point 0, 1, at the point 1, 1, and maybe at the point 1, 2. Let's get these 3 vectors. So at 0, 1, I plug in 0 for x, 1 for y, and so I'm going to get 0 minus 2. That's my first R2 vector. We know how to plot that. We know what it looks like. I go, if it doesn't say otherwise, you're always starting at the origin. And I go 0 in the x, negative 2 in the y. So it'd be down like this. But I did this gradient at the point x equals 0, 1. So I'm really going to start at the point 0, 1, which would be here. So I really want to draw that from here, that vector from here to here. It's minus 1, that's positive 1. Okay, let's put in a few more. What is at the point 1, 1? So we'd start here and we draw this vector. When x is 1, I get minus 2 in the first component. When y is 1, I get minus 2 in the second component. So I'm now going to draw the vector from the point 1, 1 in the direction minus 2, minus 2. So I start at the point 1, 1. I go minus 2 along the x, minus 2 along the y, and I'd be here. One more. At the point 1, 2. So when x is 1, I'll get minus 2. When y is 2, I'll get minus 4. So I'm going to start at the point 1, 2. And I'll go -2 in the x, -4 in the y, and it would be down like this. Okay, we could label each one of those, like that last one was the gradient of f at 1, 2. And it was -2, -4. Right, you could put a bunch of those, right? It'd be easy to put a bunch of these on one graph. And in fact, that is something called the gradient vector field. If I was to draw at, like, I only drew this at 3 different points, but suppose I drew this at 9 points, like I also check here, and here, and here, 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 here. All these different starting points, right? I could try a grid, overlay a grid of points, calculate the gradient at every one of those, and I'll have a bunch of vectors pointing in different directions. They have direction and length. What is that actually going to mean? Well, the first thing is if I were to do that, I get something called a gradient vector field. I'm putting all my vectors on the R2 field, all my gradient vectors on a field, makes a gradient vector field. We're going to spend a lot more time again in book 3.5 on vector fields. We'll just hit them briefly here when we stop to talk about gradients here in book 3. Okay, so we're going to come back to gradient vector fields. For now, I want to focus on what these gradient vectors actually mean. So let's make some space over here maybe for a picture of our surface. So our R3 surface is this circular paraboloid, so it's like this mountaintop here. And at 0, 1, so 0 along the x, 1 along the y, and you actually go up to the surface, so f at 0, 1 is what's the z value there. So again, I'm focusing on when x is 1, I'm sorry, when x is 0, y is 1, what is z? So I plug in, we get 6 minus 0 minus 1, so 5. So I'm actually at the point 0 along the x, 1 along the y, 5 here. So it'd be somewhere on this surface, 0, 1, 5. So at that point on the surface, what this gradient vector is telling you, it's an orientation. So we were here at this point, let me just put it in red, highlight it a little bit better. We had this vector. So again, that's down here in our skewed XY plane. I'm actually up on the surface, but if I was up on the surface and I had a compass in my hand, that compass is like pointing you in a 2D direction, right, to move. And this compass would point us, the gradient is telling you, go 0 in the x, minus 2 in the y. So I'm up at this point here, and I go in the negative y direction, nothing in the x direction. So it'd be pointing us like that way. In which case, it's pointing us uphill. And that's always going to happen. That's what's so neat about the gradient, is the gradient, besides being a vector of first partials, it is also the direction of steepest ascent. And that also gives you a clue as to why we usually focus on R3 surfaces. So this was the surface we started with. It's an R3 surface. At any point, you can stop and compute your gradient. It's a vector of first partials. You can evaluate that gradient at that point, and you get a vector. We did it here 3 times. What that vector means is it's where you should go, the direction you should walk if you want to get to the mountaintop quickest. And it's a direction of steepest ascent, and this is key locally. Like most things with the derivative, think back to R2, they were good local, they gave you good local information about a function. Here, we're thinking about surfaces. That function is a surface rather than just a 2-dimensional curve. So now we have a surface, and when I compute a gradient, it gives me this direction to walk to get to the nearest peak. So in local information. It might not be a global peak, but it's the direction of steepest ascent. What do you think you would do if you wanted the direction of steepest descent? So here, it said start walking 0, -2. So go in the negative y direction. Well, don't you think, again, if you had your compass and you wanted to go, instead of looking uphill, up a mountain, you just turn in the completely opposite 180-degree direction, and you'd be walking downhill. And that's the case on this mountaintop too. We'd be walking downhill. And how we did that was if we just negated this. So what is the negative gradient at 0, 1? You just negate the values in your vector. And it says start walking in the positive y direction, and that would be going descent. So, summary. The gradient vector, grad f, or just upside down triangle f, is the direction of steepest ascent locally. But the negative gradient is the direction of steepest descent locally. In this case, the surface is pretty simple, so just continue walking that way. You will get to the mountaintop. There aren't any undulations and things that you'd have to maybe reassess, but on more complicated surfaces you would. In the direction of steepest ascent or descent, you'd have to walk a few paces, reevaluate, turn, walk a few paces, get another gradient, maybe it will redirect you a little bit. And if you kept doing that iteratively, you would get a path of steepest ascent or steepest descent, depending on which one you follow, the positive or the negative gradient. Okay. So maybe let's take a look let's look at a surface here. So I'm going to do a screen share. And let's go to CalcPlot 3D. Okay, so we do have a surface here. And we've got this little tip. We can just use our arrows and move it around and kind of see that there are two spots here. We've got like what looks like around here a global min and a global max. And we'll get to those words, but you understand those from Calc 1 and Calc 2 generally. And anything else about this surface? Yeah, okay, so we could stop and compute gradients at any point. And what I want to show you something with CalcPlot 3D is in this little arrow, you can ask to show the gradient at a point on the surface. And then in this 2D area, you can pick the point that you want to take a look at and move it around and watch as the gradient moves on the surface. And so again, the gradient is shown like we plotted it back here. You're plotting a 2D vector, so in the XY plane, but what that translates to a point and a vector on the R3 surface over here. So again, if you were on this surface, it's saying walk. If you can kind of see the vector back here, and I turn it around, you can see that if you do walk in that direction, you would be going up the hill, right? So you can play around with different surfaces, ones from your book, ones that are input from CalcPlot 3D, and see what the gradient vector is doing. The other thing to notice as you move this around, you look at the top of the screen and it's showing you two things. In blue is the point you're at. So let's move to a point a little bit better. Okay, so this is about the point 1 along the x, about -1 along the y. This is the height, the z value there. That's the blue point on the surface. But it also, right above that in green, shows you the gradient at that point. At the point x is 1, y is about -1. It shows it in this vector form. And we did a little bit of this in chapter 1. It has an I and a j component because it's an R2 vector. But that would be written like for us, the same thing as the gradient of 1 approximately -1 is -0.4344 about and -0.89. So that's saying the same thing, just with IJs. Okay, let me double check, make sure there's anything else I wanted to say about gradients. So gradients give you directions. We know how to compute gradients, and you can get paths of steepest ascent. Oh yeah, that's one last thing I need to say then. how are gradients related to the contour map? So we'll pause this for a moment. Clean. Okay, so gradients have this relationship to a contour plot. So let's think for a moment, and then we'll use a tool to help us. But let's think about this surface again. What is its contour plot going to look like? Maybe you know, you should at this point be pretty close to having that on the top of your head. You did a couple activities on contour plots and topo maps at the end of chapter 1. And we remember that contour maps are made from level curves, which are z equals k planes that slice through your surface and then get projected down. So we should imagine in the xy plane, what should this look like? It should have a bunch of rings, right? And they should be tighter and then maybe more widely spaced as we get, that's a terrible circle, closer, right? And each one of those will have a label. And we know how to do that explicitly by hand, but let's jump to contour CalcPlot 3D and see the contour map there. So we entered this surface in right here. So 6 minus x caret squared minus y squared, put it from -2 to 2, hit this red button, shows us the contour plot with the level curves labeled. Again, fits what we saw in our picture here. We knew they had to be rings. It's a circular parabola, and they should be increasing as they get towards the origin, which they are. 6 right here, right at the origin, 5, 4, and so on. Now, what's still left on here was the last time when I clicked on this little arrow and did the gradient at a point. Well, that's back to the surface. So again, you can see, and you can see the level curves right there with their values. But we want to come back to this view in the contour plot. Oh, get out of that. Back to our contour plot, and I want to move this point around and show you something. So it keeps coming back to the 3D. I want to move it, but let's go over here then and look at it. Might be a better view. So I'm going to move the point that I'm choosing. And what do you notice about the gradient vector every time, no matter where I move it? What is its relationship to the level curve that it's on? Right, so I'm right here around the z equals 3 curve, and I just keep following that. Or maybe I jump over here to the z equals 4 curve, move along that, or I'm moving this way. And there are infinitely many level curves that aren't drawn, right? But between the 4 and 5, there's a 4.5, a 4.7, right? There's many there. What do you notice every time about this level curve? It's always perpendicular. The gradient is always perpendicular to the level curve. That will always, always happen. That's a really neat property and relationship between the gradient and the level curve. It's something you would prove if you're a math major, especially if you took a graduate class in calculus. You'll be able to prove that relationship, and we're going to use that. So let me just stop the screen share for a moment and write that on the board. The key point is that the gradient is perpendicular, or we often know that the synonym is orthogonal, perpendicular to the level curve. So this is how you can draw, using this property, is how you can draw what's called a path of steepest ascent or descent. And you're going to do this in a couple activities in your journal. This is a really simple one. There's not much to do here, but I would start at any point, let's say the point I want to start at, and I'd go a few steps in the direction of the gradient. Well, the gradient is always perpendicular to the level curve. I'd get to this next point, and I'd take a few steps in the direction of the gradient, which is still the same direction. Again, very easy to see that this one's going just right into the origin, and it doesn't change. But if we do a screen share, maybe pick one of the more interesting figures that are already preloaded in CalcPlot 3D, we'll see. Let's turn that one off and go to, I thought we had another one. Let's enter a new one. Oh, that's easy probably. Let's do another one. Let's see what this guy looks like. Oh, that's a pretty wild surface. Oh, wow. Huh. Let's try another one. I like the one I just had. That's ours. Oh, that's pretty cool too. Kind of got like a twisted plane that got warped and twisted. Well, let's look at this contour plot. Wild, huh? Okay, probably not one I'm going to look at. Let me reload this. Yeah, let's look at this guy. Okay, so this surface, let's go to its contour plot. Cool contour plot, and we can see that there were those peaks and valleys in that surface. And let's turn on the gradients again. Here. That's cool again, showing us the level curves on the surface. And there's our contour plot to the left. Let's click on this little down arrow and see the gradient at a point on the surface. And you can see it now happening both in the two-dimensional contour plot on the left over here and on the surface over here, what's happening. And again, that follow the orthogonality principle. So every time I do this, it's always orthogonal to the level curve that I'm near. But you can also do something like figuring out the path of steepest ascent. So clearly this one would be going to the peak right here, right? Because these are increasing 0.2, 0.6, 0.8, 0.1 all the way up into here. So that's a peak. And if I wanted to ascend, what is the path that I would do it quickest? You wouldn't actually go straight like this. You would follow the direction of the gradient. The gradient's actually saying, first walk a little bit here. And so I'm going to do that and go to get to this point. And then it's telling me to walk in this direction, and I continue in that direction until I got there. So you can imagine putting a bunch of little points here, go to where that ended, here, here, and iteratively climbing your way up by reassessing the gradient at every point. You could try, maybe you actually started over here in the valley, right? So I'm down in the valley here, and it's telling me to walk. Okay, I'll do a few steps to get to there. It's still saying go that way. Still saying go that way. Now it's starting to slightly turn, and you can see your path coming around out of the valley, up the hill. And again, that's what you're going to do when you're using that orthogonality principle to find the path, estimate the path of steepest ascent or descent. If you want a descent, you would just go the opposite of this, right? This is always showing you the positive gradient. So if I wanted to start in the peak and descend, I would go this direction. Just go the negative of the gradient each time. Stop the screen share. Okay, that's the last piece about gradients and the key concepts. So quickly summarize, gradient is a vector of first partials. If we're talking about an R3 surface, we'll have a vector, a 2D vector that we can plot in the XY plane. We plot a whole bunch of those, we get a gradient vector field. Every gradient can be evaluated at a point. At that point, it's telling you the direction of steepest ascent if you use the positive gradient. If you just negate it, which would mean pointing 180 degrees in the other direction, that'll give you the direction of steepest descent locally. When you string a bunch of those together iteratively, you get a path of steepest ascent or steepest descent. All right, thank you.